So in this video, we're going to look at kinetic molecular theory. Well, we're going to look at one of the results that we got. So we're going to look at calculations involving the root mean squared velocity, right? That would be URMS, root mean squared velocity of gas molecules. So we're going to look at calculations involving that equation. So one of the results we got from the kinetic molecular theory analysis was this equation, that the root mean squared velocity is equal to the square root of 3 times the gas constant R times the temperature in Kelvin divided by the molar mass. But before we can use this equation, we have to consider the units of all of these things because the units have to work out right. So the first thing we're going to look at is the units of the root mean squared velocity. Those units should be meters per second. Okay? So the root mean squared velocity is measured in meters per second. Now, the other thing we can really evaluate here is the gas constant R, right? The units of R, when it's given in energy terms, right? R equals 8.314 joules per mole Kelvin, right? So let's focus first on analysis of the joules unit, right? So joules are a unit of energy, right? And energy is also has the same units as work. Okay? Energy and work have the same units, right? So work equals a force applied times the distance over which it is applied, right? Which give us units of newtons times meters, right? So newtons are a unit of force, right? And so force equals mass times acceleration. And so those are units of, right, kilograms, and acceleration is in meters per second squared, right? So those are our units of force. So if we take our units of force and put them up here, right, then our units of work, right, become kilograms meters per second squared times meters is kilograms meters squared per second squared. And that unit of work is the joule. So the joule is equal to units of kilograms meters squared per second squared. Okay? So let's look at our equation here in terms of units, because this is the thing we haven't addressed yet. Okay, so let's look at this, I think, on a clean sheet of paper. Let's move to a new sheet. Okay, so let's look at a unit analysis of this, right? So the root mean squared velocity has to be in meters per second, right? And so inside here, right, there's a 3, which doesn't have units, right? R is in units of, the joules is kilograms meters squared per second squared, but that's joules per mole Kelvin, right? So all of those are the units of R. T is in units of Kelvin, and we still haven't decided what our units of the molar mass have to be. So let me extend my radical sign to include everything here. Okay? So let's look at this and see what we can get rid of. Right? So we've got Kelvin divided by Kelvin. That can go. Right? We've got a meter squared per second squared that if we take the square root of can give us our meters per second. So the big key here is looking at, right, this is kilograms per mole. And that unit doesn't appear over here. So it's the kilograms per mole we've got to get rid of, right? So let's condense this a little bit, right? We've still got our 3. We've got kilograms per mole, and we've got meters squared per second squared left. And so that means the units, right? This is all inside a square root sign, right? And so we've already said if we take the square root of something meters squared per second squared, we can get meters per second. But we've got to get rid of this kilogram unit and this mole unit because they don't appear here, which means the unit of the molar mass must also be in kilograms per mole. It's only if it's kilograms per mole that those cancel, leaving us our proper unit here so that when we take the square root of it, we get the proper unit of our root mean squared velocity, right? So in using this equation, right, therefore, the molar mass must be expressed in units of kilograms per mole, right? Not grams per mole. To cancel that kilogram unit hidden in the joule unit in our gas constant R. So that puts some limitations on how we approach these problems, right? We have to get the units right. Everything has to cancel to leave us with the units we need to get the proper units for our root mean squared velocity. So let's determine the root mean squared velocity for nitrogen gas at 300 Kelvin, right? Now, the molar mass of nitrogen gas is 28.01 grams per mole, but we know that that 1 kilogram is 1,000 grams, so that equals 0.02801 kilograms per mole, right? And that's the proper unit to use in this equation. right? So the U, root mean squared, for nitrogen is going to be equal to the square root of 3 times the gas constant R, 8.314 joules per mole Kelvin. We've already shown how those units cancel, right? Times 300 Kelvin divided by 0.02801 kilograms per mole, right? And if we do all of that, we've shown that the units cancel, right? So we get that that is equal to the square root of 267,140, and that's meters squared per second squared. If we cancel our units, if we take the square root of that, we get 516.9 meters per second equals the root mean squared velocity, that is the average speed of molecules in nitrogen gas at this warm temperature, right? 300 Kelvin is, a little warmer than room temperature. All right, that would be in a warm room, but not hot. Okay? And so, right, nitrogen travels on average about 517 meters per second in a warm room. Right? That's how we do those calculations. So here, let's do the same calculation, but with helium at 300 Kelvin. The big difference is that helium has a molar mass of 4.0026 grams per mole. If we express that in kilograms, it's 0.0040026 kilograms per mole. Right? And so if we put that into our equation, we get a root mean square velocity when we calculate it out of 1,367 meters per second. Right? Now remember, right, that the root mean square velocity for nitrogen was only 516.9 meters per second, right? So at the same temperature, right, both were determined at 300 Kelvin, right? Helium is moving substantially faster than nitrogen, even though, remember, at 300 Kelvin, they have the same kinetic energy. But since helium's smaller, it must move faster to reach that same kinetic energy. And so this has some effects. Early in the space program, someone had the bright idea of replacing the nitrogen in the atmosphere with helium, thinking it would be safer because helium is inert and helium is lighter, so they would carry less weight. But helium is moving so much faster, it collides with the skin more often. Every collision takes a little heat away. So the helium atmosphere was making the astronauts feel colder even though the temperature was the same because there were so many more collisions. Okay? Now, if we consider the same thing with argon, and I'm going to try to add it to this slide, and then I will come back. So now I have added the root mean square velocity calculation for argon. The big difference is that argon has a molar mass of 39.948 grams per mole, or 0.039948 kilograms per mole. And when we do that calculation, we end up with a root mean squared velocity of only 432.8 meters per second, right? Slower, right? The heaviest gas moves the slowest. Now, this is important, right? If you have double pane windows, right, where you've got two panes of glass, they tend to put argon gas in between those panes of glass. Argon moving the slowest has the fewest collisions with the glass, right? And so it slows the conduction of heat across the gap between the glass. Okay? And so that's one of the ways that we have improved the efficiency of windows. We create a gap. We put a slow-moving gas in the space for that, between that gap between the two panes of glass. And the slower moving gas, because it has fewer collisions, it has fewer opportunities to pick up heat on one side and transmit it to the other, and it slows the conduction of heat. Right? So there is the practical application of knowing the root mean square velocities. The big thing is remembering the units for the molar mass have to be in kilograms per mole, right? That's essential when you're doing these problems.